And we have our next speaker, which is Haqq-Misra. I hope I have pronounced it correctly. If not, please correct me. And he's going to tell us about the extraterrestrial pollution. Did I have it searched for extraterrestrial pollution? So very intriguing topic. And please, the floor is yours. I will tell you when it will be about 10 to 12 minutes into your presentation.
Okay, thank you so much, Anna, and thank you, Tomas, for organizing and inviting me. So I'm Jacob Haqq-Misra. It's great to meet all of you. I'm from the Blue Marble Space Institute of Science, which is how I found my way to this workshop. And it's been great to hear about all the work that you've been doing. So in this biosignature session, it seems like from looking at the abstract, a lot of the other biosignature talks focus on looking for biosignatures on Mars with ongoing Mars exploration. And so this talk, I'm going to focus on exoplanet biosignatures. How can we look for evidence of biosignatures on another planet, orbiting another star, using space telescopes and spectroscopy and things like that. And I'm specifically going to focus on pollution. But what I want to emphasize is when I say technosignatures, I mean evidence of technology that we could detect using the tools of astronomy. But technosignatures and biosignatures are two sides of the same coin. It's not an either or. We want to find life. We want to find, and in this case, I'm talking about life on exoplanets. So that as an astrobiologist, that's what I'm interested in. And so if evidence of life is something like water vapor and methane and ozone in the atmosphere of an exoplanet, well, that's really exciting. That's evidence of life. If the evidence of life is, pollution or satellite debris or something around an exoplanet, that's also evidence of life. It's technology, but it's life that made the technology. So, I just like to make this point at the beginning of these talks that what I'm talking about is a subset of biosignatures, but it's the kind of biosignatures that are the result of technological processes on the planet. And in some cases, technosignatures might be more detectable than other kinds of biosignatures, or at least if they're not more detectable, they might be less ambiguous. There's a lot of ways the planet can make oxygen, for example, maybe not as many ways to make some of these technosignatures. So the rest of this talk, I'm going to show you some examples of technosignatures that myself and my collaborators have been studying with the idea of trying to build up the science of technosignatures to the point where biosignatures is right now, where you've got major space telescope missions that are largely motivated by this search for biosignatures. And so here's the James Webb Space Telescope. Fortunately, this is up and collecting data now. There's the MIRI mid-infrared spectrometer on the James Webb Space Telescope. So this will be one of the really the first opportunities to get to peer into the atmosphere of an exoplanet. We're not going to be able to do a lot of them with the James Webb Space Telescope, but TRAPPIST-1 system and TRAPPIST-1e is probably the good habitable planet. We're going to get a look at least at that planet, maybe a couple others, and get some data finally as to what kinds of atmospheres do these planets have and what's in their atmospheres. I'm not going to talk in detail about those methods, but if you're interested, you can send me a message. And there's lots online about how transit spectroscopy is done. So just look for transit spectroscopy. But it's not that important for this talk. Just if you understand that we can use space telescopes not just to detect extrasolar planets, but also to start characterizing their atmospheres, to get information about what gases are in their atmospheres. I'm going to talk about two things in this talk. The first thing is halocarbons, the technosignatures, and then nitrogen species. Halocarbons, what do I mean by halocarbons? These are these molecules that are implicated in the destruction of the ozone layer. So you can see plot here, the total ozone in Dobson units, and there was a the ozone hole was actually discovered around the 1980s, but then it continued to deplete even when there was legislation, a treaty passed to ban the production of these chlorofluorocarbons, or the halocarbons. But then ozone levels have been steadily rising, and they're projected to recover to pre-1980s levels, but not till 2060. So it takes a while. But in general, this was a success story for scientists detecting a problem in the Earth system, treaty being accepted, changes being made, and now the ozone hole is recovering. So you can see here on the left is CFC11. There's just various types of chlorofluorocarbons. So these are just two different molecules, CFC11 and 12. They're two very potent greenhouse gases. They have very long lifetimes in the atmosphere. So you can see the solid line shows the historical measurements of these two chlorofluorocarbons in the atmosphere. And you can see the Montreal Protocol. This is the treaty that banned these compounds because of their role in ozone layer destruction. Shortly after the treaty was passed, these values taper off and start to decrease. And they're still in the atmosphere, but they're not being produced as much, and so they're decreasing. So you could imagine, like, well, what if we hadn't passed the Montreal Protocol? Maybe CFC levels would have continued increasing. It looks like it was kind of a linear trajectory up until then. So you could imagine that even though CFC levels are lower today than they were a couple decades ago, you could imagine an alternate scenario where they're actually quite a bit higher than today had we not had this treaty. And so we ask ourselves, well, what if aliens were looking at us, alien astronomers pointing their James Webb Space Telescope at Earth, or vice versa, we're looking at extrasolar planets. Maybe there's life out there that has technology. If we saw something like chlorofluorocarbons, we don't know of any other kind of biology that makes that. So it would be good evidence for technology. And so, we can look at the absorption cross-section of these two gases, just where, what wavelengths do they absorb strongly at? It's this near mid-infrared region between 8 to 14 microns. You've got strong absorption features for both of these gases. So this is the kind of thing you would look for with the James Webb Space Telescope with the spectrometer on it. And so we just did some simulations. We did climate simulations, and then this is the synthetic spectra that you would see if you were pointing the James Webb Space Telescope at TRAPPIST-1e. If there's no chlorofluorocarbons on TRAPPIST-1e, but it otherwise has an Earth-like planet, there's a lot of assumptions here. So we're just trying to calculate detectability limits. So an Earth-like planet, it's this green line. That's the base reading. No chlorofluorocarbons. But then you can see the 1x, 2 times, and 5 times the amount of chlorofluorocarbons. You see these strong absorption features that are due specifically to the chlorofluorocarbons. It increases your contrast between the star and the planet. And so, you can imagine trying to observe this. Now you've got, a noise floor on these instruments. How much can you see before the noise starts to get overwhelming? But so you go look on the left here, on the bottom is the amount of observation time you have. On the upper, the vertical axis is the signal to noise ratio. So if you want a signal to noise ratio of about 3, well then, you follow the line over 3 intersects with the red curve at about 10 hours. So if there's 5 times the amount of CFCs, you could detect that. It intersects, 2x at about 30, 40 hours, and the 1x, about 100 hours. So it's doable. This is the kind of thing that we're not saying like let's put all our money into searching for CFCs around TRAPPIST-1e. What we're saying is if you're looking at TRAPPIST-1e anyway, because you care about looking for biosignatures and you're going to look for a long time, well, one thing we should keep in mind is the possibility that you're going to see something weird like CFCs. And it's certainly doable if you're going to put a lot of time into a system anyway, then you're going to be approaching the amount of time you might need to see something like this. So, the point is not to say we're going to find this on TRAPPIST-1e, but rather we are at the technological ability to look for technology in the atmospheres of other planets. And it might be about the same level of challenge as looking for other kinds of biosignatures. So that's really the point here. So the second part, I'm going to talk about nitrogen species as technosignatures. So chlorofluorocarbons, the nice part is we don't know about anything else that makes chlorofluorocarbons. So as far as we know, there could be other biology, other non-biology even that makes CFCs. We don't know. But as far as we know on Earth, chlorofluorocarbons are the product of technology. So nitrogen species are not always the product of biology, but there are cases where on Earth we are enhancing the production of nitrogen species, and that could be a technosignature. So here is back in 2020 when the pandemic was brand fresh and new and we were still trying to figure out what was going on. Here's a satellite image of China before and after Chinese lockdowns. And we were looking specifically at images of satellite image nitrogen dioxide. And so on the left, we have lots of nitrogen dioxide around major cities, especially Beijing, but also other major cities. And then after the lockdown, very, very little. This is largely associated with cars on the road. And NO2, nitrogen dioxide, is a byproduct of combustion. So myself and Ravi Koparapu, my collaborator, we looked at this following the pandemic and said, like, oh, I guess this is a technosignature. Now we know NO2 is made by other biology, but about half of the nitrogen dioxide emissions, half to 3/4 on Earth, are from combustion, from human activity. So it's a technosignature in the sense that a lot of our NO2 would not be there if not for human technology. We can look and see, where does nitrogen dioxide have some strong features, and you can see this between 0.2 and 0.6 microns. So this is in the visible part of the spectrum. There's nitrogen dioxide. There's also some here, longer wavelengths, 3 to 16. But on the right panel, you can see those 3 to 16 wavelength features have a lot of overlap with oxygen and water and CO2 and other things. But in the visible part of the spectrum between 0.2 and 0.6, there's not a lot of other overlap. So that's a good place to look to see, is there nitrogen dioxide? So the James Webb Space Telescope may not be the best for that, but the next generation of space telescopes, the LUVOIR and HABEX, the large ultraviolet optical infrared observer that NASA was recommended to build, would be great for this. And maybe there'd be some other ground-based facilities too that could do this. But so here's another idea. Let's look for nitrogen dioxide on the atmosphere of an exoplanet.
13 minutes.
Okay, thank you. So, you could look at different star types. I might not spend too much time on this one, but on the right side, you can just see there's different spectra for different stars. The sun has more visible light. A K-dwarf star, an orange dwarf, puts out a little less in the visible, and an M dwarf, red dwarf star, puts out more in the infrared. So that just leads to different photochemistry. And if you look on the left plot, the blue line, if you follow it up to high altitudes, the blue line shows not a lot of NO2 in the upper atmosphere. But if you look at the sort of pink and green curves for the K-dwarf and the M dwarf, you get more NO2 in the upper atmosphere because there's not as many visible, ultraviolet photons to destroy it, so it builds up at higher levels. So just the point of this is just looking at other stellar types, lower mass stars might actually have higher abundances of nitrogen dioxide than accumulate on Earth. And so we could think about looking for nitrogen dioxide. On the right plot, you can see just observation time hours versus the signal to noise. And so if we have Earth-like levels of NO2 and you've got this 15-meter space telescope, you could see this at a distance of 10 parsecs, signal to noise ratio of 5. It's going to take about 600 hours or so. On the left plot, we've got different scenarios here based on the different noise threshold. But, again, the point is in hundreds of hours, which is a lot. But some of these deep field images that the Hubble and other space telescopes have done have been hundreds of hours of observation time to get some of these very faint signals. So again, we're not saying all the money should be prioritized to do this, but if you're going to look at exoplanets at high precision, high detail, for these long integration times, let's keep in mind the fact that these are some of the things we could find, some weird anomalous technosignatures that might be the first evidence of extraterrestrial life we find. So very quickly, I'll just mention one final example of a technosignature is agriculture. And you don't think of that as a technology necessarily, but we are managing our nitrogen cycle, and that is a large part of what agriculture is about. So agriculture puts nitrogen compounds into the atmosphere. Here's a satellite image showing ammonia emissions that are largely concentrated over agriculture intensive areas of the world. The ammonia is coming from the production of fertilizer. We take nitrogen from the air, hydrogen, gas, you have this industrial process that's high temperature, high pressure, and you produce ammonia. This is where a lot of our fertilizer comes from. And you can see this Haber-Bosch process is what it's called. Following the invention of that, the population of the world swelled enormously to the billions of people we have today. So we are literally eating our air. We are eating air by turning it into fertilizer, and you have to saturate the field, and so the excess ammonia makes it up into the atmosphere and becomes nitrogen gases. So, you could detect this. Here we just did some calculations as to what if there was 30 billion or 100 billion people on Earth. You would increase the amount of nitrogen compounds. You just see these dotted lines here. That's just showing you have more absorption at certain wavelengths that some of these space telescopes could look. Here's just another version of the same thing. You see that's ammonia, methane, nitrous oxide. Those three gases would be associated with intensive agriculture. We see these on Earth today, and so higher agricultural production, you would see even more on an exoplanet. And this is something that could last for geologic time. You could do this sustainably, and it would not be a problem. So, that's kind of what I wanted to do, is give you a survey of some of the technosignatures we've been thinking about. There's halocarbons, there's product of combustion, there's agriculture. We need more ideas. We're at the infancy of this state, of this field. We need to have a lot of different ideas for the types of technosignatures that these new space telescopes would be able to find. And that'll help get the field of technosignatures to the point where other biosignatures are today. And we can really start tying it in more towards relevance towards upcoming and future missions. So thank you very much.
Very interesting talk, and I think that your requests have been already granted in our discussion section. There are a couple of different suggestions for what else can we look for as techno indicators, techno markers, not biomarkers. So do you have any comments on any of the ideas that have been proposed? For example, Marek Elowitz is suggesting looking for 4 different, numerous different compounds that can be visible in the infrared spectral region.
Oh yeah, absolutely. So yeah, Mark is right. These are all great ideas, and I definitely was not trying to cover all of them, but there are some papers that have talked about some of these other artificial gases, especially some that you could use if you wanted to terraform your planet to make it more, we might terraform Mars to make it more Earth-like. You might use some of these other gases, SF6, for example, could be. I saw someone asked about nuclear power technosignatures. I've actually got a paper, I'm working on that. Like, would radioactive fallout be a technosignature? It wouldn't last very long, so you'd have to continually having explosions. But it might. I see Mark says search for nighttime lights. So then absolutely, people have written papers about this, and LUVOIR, HABEX type mission might be able to find city lights. So these are absolutely great ideas. Forestry is a great idea, and that kind of shows that the divide between biosignature and technosignature is kind of blurry. Just like I pointed out, agriculture can be a technosignature. I mean, forestry, what you're going to notice is the red edge, infrared absorption, or the reflectance spectrum in the infrared from chlorophyll, which would look like a biosignature. But if you could find something to understand that that's actually being actively managed, then that might look like a technosignature. So that can certainly be somewhere on the boundary between there.
Perfect. Unfortunately, very interesting topic, but we need to move on to our last talk of the session, and I hope you can continue the discussion in the chat.